Good morning to all. I am Prabhavathy, Assistant Professor, A.D.M.College, Nagapattinam. We already seen about number theory modules. Today, I am going to explain about perfect numbers. What do you mean by perfect number? A positive integer, that is a natural number, is called a perfect number if and only if it is equal to the sum of its divisor excluding itself. That is sum of its proper divisors. For example, let us take 6. The divisors of 6 are 1, 2, 3 and 6. And if we add all these numbers, we will get 12. That is 2 times 6. So, 6 is a perfect number. So, 28, 4, 96 are all perfect numbers. Now, let us use the notation sigma of n. That is sum of divisors of n including n. So, if sigma of n minus n is nothing but sigma of all divisors of n excluding n. So, if n is perfect number, then the sum of the proper divisors, that is sum of all the divisors excluding n, is nothing but sigma of n minus n, which is equal to n by definition of perfect number. If we take the minus n to the right hand side, we will get sigma of n equal to 2n. That is an integer, a positive integer, or that is a natural number, is perfect if and only if sigma of n, that is sum of all the divisors of n, should be equal to 2n. Now, let me give the proof of Euclid's theorem, which deals about the generation of perfect number. If 2 power p minus 1 is prime, then 2 power p minus 1 into 2 power p minus 1, the product of the numbers, is a perfect number. Let me explain the proof. Now let us take n is equal to 2 power p minus 1 into 2 power p minus 1, and we are given that 2 power p minus 1 is a prime number. That means it has only two divisors, 1 and itself, that is 1 and 2 power p minus 1. So what will be the sum of the divisor? That is sigma of 2 power p minus 1 is sum of these two numbers, 1 and 2 power p minus 1. If we add these two numbers, we will get 2 power p, which is power of 2. It is an even number. And now we observe that the numbers 2 power p minus 1 and 2 power p the whole minus 1 are co-primes, that is relatively primes. That is the GCD are 1. Now let me calculate sigma of n. Then sigma of n is nothing but sigma of 2 power p minus 1 into 2 power p minus 1. Since they are relatively primes, co-primes, so that sigma of 2 power p minus 1 into 2 power p minus 1 can be written as sigma of 2 power p minus 1 into sigma of 2 power p the whole minus 1. And now by the definition of the sum of the divisor, sigma of 2 power p minus 1 is nothing but 2 power p minus 1 plus 1 minus 1 by 2 minus 1 into, since 2 power p minus 1 is a prime, so that sigma is nothing but 2 power p. So using the calculation, we observe that this is nothing but 2 power p minus 1 into 2 power p. Now let me write the 2 power p as 2 into 2 power p minus 1, because we know that a power mn is nothing but a power m into a power n. So using the fact that we can rewrite this 2 power p as 2 into 2 power p minus 1 and the next term 2 power p the whole minus 1. So we know that the n is nothing but 2 power p minus 1 into 2 power p the whole minus 1. So this can be written as 2n. So left hand side is sigma of n, right hand side is 2n. So now we take n is in the form 2 power p minus 1 into 2 power p the whole minus 1. So the summation of all the divisors of n including n, that is sigma of n, is 2n. Hence n is a perfect number by definition of perfect number. So now let us see some remarks. In last module we discussed about Mrs.M.Prabhavathy theorem. That means 2 power p minus 1 is prime only if p is prime. Also if p is prime, then 2 power p the whole minus 1 need not be a prime number. So now we see the Euclid theorem. In that case, both terms p and 2 power p whole minus 1 must be primes. So let us see some examples. That is, if you take p as 2, 3, 5, 7, 11, 13, the 2 power p minus 1 will be 3, 7, 31, 127, 2047 and 8191. So the corresponding n, that is 2 power p minus 1 into 2 power p the whole minus 1 will give you the values. For p equal to 2 it will be 6, for p equal to 3 it will be 28, for p equal to 5 it will be 496 and so on. And we see that in the place of 11 we are giving question mark, because when p equal to 11, if you calculate 2 power p the whole minus 1 is nothing but 2047. It can be written as product of two numbers, that is 23 into 89. Both are less than 2047 and greater than 1. That means 2047 has more than 2 divisors. So it cannot be prime. So it is not prime. So according to Euclid's theorem, the corresponding n cannot be perfect number. So other numbers are 5 perfect numbers. Now, how can we find the perfect numbers? So we can use the Euclid's formula, that is 2 power p minus 1 into 2 power p the whole minus 1. And some authors found that the following prime numbers give you the 24 perfect numbers, that is 2, 3, 5, 7 and so on. Next. So now perfect numbers given by the Euclid's formula are clearly even number, because it is the product of power of 2 into something. So there is a question, does there exist odd perfect numbers? So far no such number has been found. It has been verified that there is no odd perfect numbers up to the number 10 power 50. Perhaps there may be any no at all. So Euclid conjectured that the converse of his theorem is also true. However, Euler proved that it is true only for even perfect numbers. Next. So now we will prove the converse of Euclid's theorem. That means if a number is a perfect number, then it should be of the form 2 power p minus 1 into 2 power p the whole minus 1, where 2 power p the whole minus 1 is a prime number. Now let me see the proof. Next. So let n be uneven perfect number. Then what is the definition of perfect number? That sigma of n, the sum of all the divisors of n should be 2n. So we are taking n as an even perfect number. So it may be power of 2 or combination of power of 2 and some odd numbers. Let me take the general form. Take m is equal to 2 power k into m, where m is an odd number and k is greater than or equal to 1. Since sigma of m, because m is an odd number, it may be prime or composite, and sigma of m should be greater than m, because m is also divisor, sigma of m should be greater than m. So we can take sigma of m is a positive integer, we take it as m plus q, where q is greater than 0. Now we are using the definition of perfect number. Since n is perfect, sigma of n is nothing but 2n. So now we replace n by 2 power k into m. So it is nothing but sigma of 2 power k into m is equal to 2 into n. So 2 power k and m are relatively prime, so it can be written as sigma of 2k into sigma of m, which is equal to 2 into, in the place of n we are replacing 2 power k into m. So now, we get 2 power k plus 1 minus 1 divided by 2 minus 1 into m plus q, which is nothing but 2 power k plus 1 into m. Now we simplify this, we will get the answer as 2 power k plus 1 into m minus m plus q times 2 power k plus 1 minus 1 equal to 2 power k plus 1 into m. If we cancel out on both sides, that is the left hand side and right hand side, we will get m is equal to q times 2 power k plus 1 minus 1. This shows that q is a divisor of m, because m is written as product of q into something, that is multiple of q. So q divisor of m, and also q should be less than m. But we are having the fact that sigma of m is equal to m plus q. So q is the sum of all the divisors of m that are less than m. That is, q is the sum of a set of numbers that also includes q, because q is the divisor of m. This is possible if the set consisting of only one number alone. Therefore, the set of divisors of m smaller than m must be 1. So, in this case, q should be equal to 1. So, sigma of m is equal to m plus q, give you as m plus 1. This shows that m is prime because prime numbers only having two divisors 1 and m, and the sum will be m plus 1. So, m should be prime number. Thus, m is equal to 2 power p minus 1, that is 2 power k plus 1 minus 1 is prime. And in the last module, we have proved one thing, that if 2 power p minus 1 is prime, then p must be prime. So, using the same theorem, we conclude here that the only number of this form can be prime, that is k plus 1 should be prime, that let me take as p. Thus, m is equal to 2 power p minus 1 is prime for some prime p. Hence, the even perfect number n is of the form 2 power p minus 1 into 2 power p the whole minus 1, where 2 power p the whole minus 1 is prime for some prime number p. So, now we are through. So, if n is a even perfect number, next, if n is a even perfect number, then it should be of the form 2 power p minus 1 into 2 power p the whole minus 1, where 2 power p the whole minus 1 is prime. So, now we see some remarks, that is, we have seen that till now no odd perfect number is found. So, in the absence of any odd perfect number, Euclid's theorem may be restated as follows. That is, a positive integer n is a perfect number if and only if n is of the form 2 power p minus 1 into 2 power p the whole minus 1, where 2 power p the whole minus 1 is prime for some prime number p. Next. So, now we will see some definition of abundant and deficient number. What are those numbers? So, we know that a positive integer n is perfect if and only if sum of n, sum of all the divisors of n is equal to 2n. Now, we have a natural question. What about the integers with sigma of n not equal to 2n? We classify these integers as follows. That is, a positive integer n is said to be abundant if sigma of n greater than 2n. For example, let us take numbers 12, 24. They are having the sum of the divisors greater than 2 times n. So, they are examples of abundant numbers. Next, we will see the definition of deficient number. A positive integer n is said to be deficient if sigma of n strictly less than 2n. Example 8, 14. Next, there is a note, that is, the set of positive integers is partitioned into 3 classes of numbers, namely perfect numbers for those sigma of n is equal to 2n, abundant numbers for those sigma of n greater than 2n, and deficient number for those numbers sigma of n is strictly less than 2n. So, according to the sum of the divisor, we are classifying the natural numbers into 3 types of numbers. Next, we will see a new class of numbers, that is friendly numbers, that are called as amicable numbers. 2 numbers are said to be amicable numbers if one is equal to the sum of the proper divisors of the other. That means we are taking all the divisors of the number excluding that number. So, that's if s of n is the sum of proper divisors of n, then n and m are amicable if s of n equal to m and s of m equal to n. Now, let us see some remarks. That is, if s of n is equal to sigma of n minus n, according to the definition of s of n, and s of m is equal to sigma of m minus m. Now, if m and n are amicable, then s of n is equal to what? M. So, m is equal to sigma of n minus n. So, in this case, sigma of n is equal to m plus n. Similarly, if m and n are amicable, s of m is equal to n. It also give you as sigma of m is equal to m plus n. So, if m and n are amicable numbers, we get the result as sigma of m equal to sigma of n equal to m plus n. That is, they should have the sum of the divisors are equal and it should be equal to m plus n. So, there are some examples. There are amicable pairs less than 10,000 are 220, 284, 1184, 1210 and so on. Next you will see some notes, that is there is no formula giving that amicable numbers. So far no amicable pair is known with one number is odd, other number is even, or both are odd numbers. Till now we found amicable numbers in which the pair of numbers both are even numbers. So next we will see the definition of triangular number. That is, a number is said to be triangular if it can be in the form n into n plus 1 by 2. See examples, 6, 10, 28 are triangle numbers. Why it is so? If you see that 6 can be written as 3 into 3 plus 1 by 2. So 3 times 4 by 2, it will be 6. 10 also written as 4 into 4 plus 1 by 2, and similarly 28 can be written as 7 into 7 plus 1 by 2. So they are examples for triangle numbers. And also we know that sum of first n natural numbers, that is 1 plus 2 plus 3 and so on up to n, is nothing but n into n plus 1 by 2. So sum of first n natural number is also an example for triangular numbers. Next, now we will see some problems related to perfect numbers, amicable numbers and so on. First problem, prove that the sum of the reciprocals of the divisors of a perfect number is 2. That is, if you take a number n, let n be any perfect number, first we should consider the divisors. It may be 1 to some d, let us take d is a divisor means, and also we can observe that 1 by d is also divisor of n. Now we are in the position to calculate the sum of the reciprocals of the divisor, and it is nothing but summation of 1 by d, where d is a divisor of n, is equal to sigma of n by n, where the summation runs through all the divisors of d of n. Since n is a perfect number, so the sum of the divisors including n, that is sigma of n, is nothing but 2 times n. Let me substitute this in the relation summation of 1 by d equal to sigma of n by n. We get summation of 1 by d, where d divides n, is nothing but 2. Next, now let me give a proof for 220 and 284 are amicable numbers. So let us take 220. By fundamental theorem of arithmetic, it can be written as product of prime factorization, prime numbers, that is 2 square into 5 power 1 into 11 power 1. Let us calculate the sum of the divisors. So sigma of 220 is nothing but by formula 2 power 2 plus 1 minus 1 divided by 2 minus 1, 5 power 1 plus 1 minus 1 by 5 minus 1, and 11 power 1 plus 1 minus 1 by 11 minus 1. So by using simple calculation, we observe that this is nothing but product of 3 numbers, 7 into 6 into 12, that is nothing but 504. So next, calculate the sum of all the divisors of 284, and we observe that the sum of the proper divisors of 224, that is excluding itself, that is s of 220, is nothing but sigma of 220 minus 220, that is 540 minus 220, which is equal to 284. So sum s of m equal to n. And now observe that 284 can be written as 2 square into 71 power 1. And let me find the sum of the divisors of 284. It will be nothing but 2 power 2 plus 1 minus 1 by 2 minus 1 into 71 power 1 plus 1 minus 1 by 71 minus 1, which is nothing but 7 into 71 power 1 plus 1 minus 1 by 70. So this gives the product of two numbers, 7 into 72. It is nothing but 504. So next, sum of the divisors of 284, that is s of 284 is nothing but, what will be the answer? 504. So therefore, sigma of 220 and sigma of 284 both are same, and they are nothing but m plus n. So m and n are amicable numbers. Now let me give the solution for next problem, that is prove that a prime number cannot be in an amicable pair. So solution, let p be any prime number. Let me take n be any other integer. If p and n are amicable numbers, then we, by the definition of amicable numbers, sigma of p should be p plus n, and but the definition of, according to the definition of prime numbers, the only divisors of p are 1 and p. So in this case, sigma of p is nothing but 1 and p. So sigma of p is equal to 1 plus p. So if we calculating these two numbers, if we observe that p plus 1 is equal to p plus n for any given integer n. If n is equal to 1, this is possible. If n is greater than 1, suppose if we take n equal to 2, then p plus 1 is equal to p plus 2. Is it true? Not. So, which is impossible. Hence, a prime number cannot be in a pair of amicable numbers. That means that except 1, a prime number cannot be friendly number with any other integer. Next final result, that if m and n are amicable numbers, then we can show that summation of the sum of all the divisors, that the reciprocals of the divisors of m, the whole inverse, plus summation of 1 by d, where d is the divisor of n, the whole inverse is equal to 1. And let me give the proof. So we already seen that. So next, if m and n are amicable numbers, then sigma of m is equal to sigma of n is equal to m plus n, according to the definition of amicable numbers. And also we know that summation of 1 by d, where d is the divisor of n, is nothing but sigma of n by n. Now we substitute the sigma of n by m plus n. Then this summation is nothing but summation of 1 by d, where d is the divisor of n, is nothing but m plus n by n. Similarly, we use the same idea. We can get summation of 1 by d, where d is the divisor of m, is equal to m plus n by n. Now we calculate the sum of the inverse, that is summation of 1 by d, the whole inverse, plus summation of 1 by d, where d is the divisor of n. The whole inverse is nothing but n by m plus n plus m by m plus n. So in the numerator is m plus n, denominator is m plus n. So it is nothing but 1. So the sum will be 1. Thank you.